Hello everyone. Today we are going to talk about the field Vane Shear test, which is the point number 6 of the chapter number 2, in-situ soil testing. Okay, so field Vane Shear test, we did from introduction to the cone penetration test, and from this video, we will start this section 6 of this chapter, field Vane Shear test. Okay, what is this test about? How is it conducted? What soil parameters can we get from this field Vane Shear test? This is what we are going to discuss in this video. Okay, so hope you will learn something. Okay, field Vane Shear test. this test, designation of American Society for Testing and Material. Okay, this is the designation of this test. Is the most common test for evaluating the underlying shear strength of soft to stiff clay. So you know already why we need, what soil parameter we can obtain from this test. This parameter, the underlying shear strength of soil, of clay, soft one to stiff one, can be obtained from this field Vane shear test. Okay, this is because the test is very rapid, easy to perform, and you can perform it in a very high speed compared to other tests. Okay, and you can repeat it anytime you want very easily. So this Vane Shear apparatus consists of 4 blades on the end of rod, the pushing rod. Okay, here is a photo of this example. These are the 4 blades. Okay, you can see this head. So here is where we can connect the rod and insert this in the ground, the Vane apparatus in the ground. Another example is this one. So as you can notice, the heads here and this are not the same. Okay, this is because the vein can be either rectangular or rectangular. This shape you can see it just okay, or tapered like this case. And here is a photo, like just a drawing that can illustrate what I just said. This type is here rectangular. You can see the base, okay, and this profile is this type. Okay, so don't think that there is only one type. Okay, there are 2 possible ways. And here is normally the height. Okay, do you see h here? This is h, is twice the diameter d. H is 2 times d. You can see d here. Okay, this is d. But in this type, the h is from here. Okay, from here to here, not from here. So this apparatus is what we are calling Vane Shear apparatus. Okay, for the field. And there are several sizes, okay, that can be used. and different shapes. The shape you already know. There are different sizes that are used, and this table is showing us the dimension of vein. Okay, and this is casing sizes, these diameters in millimeter. You can see the different sizes. H, this height or here. Okay, the thickness of the blade in millimeter mean the thickness of, for example, this one. Okay, thickness of the blade, and the diameter of rod. Okay, to connect. This is just this connection. So this D is this one. Okay, don't, this diameter is different to this diameter. This diameter here is the diameter of rod. This connection here. Okay, not same as D here. So the selection of the size of vein size is directly related to the consistency of the soil being tested. If your soil is very consistent, hard soil, maybe you will take the bigger one, the big size. Okay. So depending on the soil you are dealing with, you can select the most appropriate size. Okay. So how does it work exactly? The veins of the apparatus are pushed into the ground at the bottom of the borehole. You make your borehole and you just lower the vein and push it using rod, of course. Push it until certain depths and try to minimize the disturbance of the borehole. Here is example. This one is like under a car. Okay, the vein is coming from here. Load are coming from through here from inside the car. Okay, or you can just use your hand, rotate, or use this type of apparatus. There are many ways to push this into the ground. Okay, and for your information, this one is apparatus to perform the test in your lab. You can do it in a laboratory also. Okay, so the torque, because you are turning, rotating, trying to rotate the vein inside the soil. Okay, so the torque you will apply, you apply a torque to rotate. Okay, at the top of the rod, apply the torque to rotate the vein, and the rotation speed is following this standard, this rate. Okay, 0.1 degrees per second. Do you understand? 0.1 degrees per second. Okay, that means you have to maintain, you cannot speed up, turn it anyhow. Okay, each second 0.1. So 10 seconds, you will have 1 degree. Okay, that means in 1 minute, because 1 minute is 10 seconds, 6 times, you will have 6 degrees. Okay, so this is the standard rate for the rotation. And here is the torque. As you can see, the blade, maybe you remember the shape. Okay, when you are rotating the vein, these blades are just sharing the soil. Okay, the torque, you apply the torque, the rod here, and you will have, it will make like a cylinder. Okay, So this rotation will induce failure in the soil. This failure surface, this is failure surface. It will look like a cylinder, okay? Okay, cylindrical shape around the vein. The blade will turning and causing a shear failure in the ground. Okay, let's go now step by step to see how it works exactly. Okay, so first step is, of course, you make your borehole like this. Okay, and the vein rods connect to the vein. The dimensions are here. B is the borehole diameter. Okay, you remember for the vein, the diameter of the vein, it is D. Okay, don't forget that. H is the height of the blade, and E is thickness of the blade. Sorry, H is the height of, okay, the vein, but it can be also the height of the blade. Same. E is the thickness of the blade. Okay, so H is here, height of the vein. D is diameter of the blade, of the vein. Okay, so after that, you push using this force. Okay, you see the arrow here. This is pushing force. You push the vein into the ground, deep into the ground. At what depth? The depth D equal 4 times B. Do you remember that B is the borehole diameter, right? Okay, so from here to the bottom of the borehole should be 4 times D. Okay, so okay, yeah, so this is step 1, insertion of the vein. Okay, after doing that, after inserting the vein at the convenient depths, then what you are going to do now is to apply a torque, and of course measure that torque. You see, torque meter. You apply torque to rotate the vein in the soil. Okay, and remember that the rotation should be 0.1 degrees per second. That means in 10 seconds, you do 1 degree. Means again, 1 minute, 6 degrees. Okay, so this is what is here, 6 degrees per minute. Okay, and measure the torque. That torque you will obtain will be called like peak torque, or if you want the maximum torque the soil can have, because this torque is considered as the undisturbed, the torque of undisturbed soil. Okay, and you take note of this torque. Next step, step number 3, is to perform additional rotations with 8 to 10 revolution. Okay, 8 times or 10 times you rotate. As you can guess, when you do that, the crown will be disturbed. It will be loose. It will not have the same strength as here. Okay. Then after doing 8 to 10 revolutions, I hope you know what is revolution. Okay. You just want to 8 to 10 revolutions. Then you rotate again, but this time you measure the torque, and which will be obviously less than the one you measured here. So this means you will measure 2 torques, this one here and this one. Okay, the first one is before any disturbance, the soil is intact. Okay, the second one is after doing rotating several times, that will make the soil disturb. And you measure this one. And this one is called residual torque. Okay, peak torque and residual torque. Okay, this is the for the removed case. And then you can obtain the in-situ sensitivity of your clay, of your soil. Sensitivity test. So you divide the peak strength, shear strength, divided by the remote shear strength. Please remember that this one, the peak shear strength, we will see how to calculate the shear strength of the clay from the top. Okay, maybe it was even supposed I was even supposed to show you the formula first. But anyway, remember that from this talk, we can obtain the shear strength of our clay. Okay. And the peak torque will allow us to obtain the peak shear strength. And the residual torque will help us to obtain the remote shear strength. So doing this ratio, we obtain the sensitivity of the clay. Okay, here is an example. Again, using this machine, as you can see, it a bigger capacity machine to push this blade, this vein into the ground and rotate it. Okay, this is just after removing the vein. You can see soil is on it. Okay, let me put back this here. Torque. Okay, remember we have two types of vein. So the maximum torque, I just showed you that we can get maximum peak torque and residual torque. Okay, so this maximum torque applied will cause the failure, right? This is what we say. If we measure that torque, then this torque is a function of the declared undrained shear strength. H is, remember, the height of the vein is H, and D is this diameter of this vein. Okay, this torque is function of these two. Okay, function is a function of the undrained shear strength, H the height of the vein, and D the diameter of the vein. So we can calculate the undrained shear strength by using this ratio. The undrained shear strength is obtained from this ratio, torque divided by K, and we will see what is K. K is just a coefficient. T is the torque in Newton meters. Okay, and if your torque is in this unit, then your undrained shear strength can be obtained in this unit, the kilonewton per square meter, kilopascal. Okay, this K, this coefficient, is a constant with a magnitude depending on the dimension of and the shape of the vein. Okay, dimension and shape of your vein, because this dimension D and H, we saw previously in the table that there are different sizes. Okay, so here is a formula for this K. Okay, pi. D is just diameter, H is the height. Okay, DH again. So this is diameter of vein in centimeters. H is measured height of the vein in centimeters again. Should be in same unit, H and D. Now, sometimes you have case that it's not always the time. Actually, even here it is written that H is twice D. Okay. In that case, if H divided by D is 2, then this K can be simplified by this easily. Okay. Please, you will find a lot of formula of this, a lot of expressions of this, but it is same. It's just a matter of manipulation of this. Okay. For example, you will see we don't have, for example, to calculate the pi, for example. Okay, but here this formula is simplifying everything. Okay. If you are lucky and the H is twice the D, which is very common, then just use this K as the value of this coefficient. D, replace D by its value in centimeters, please. Okay. Don't make mistake. It should be in centimeters. Then you can calculate your undrained shear strength in this unit. Okay. So remember, you have peak torque will allow you to obtain undrained shear, the peak undrained shear strength. The residual torque will allow you to obtain the remote undrained shear strength. And then you can do the sensitivity by dividing the peak one by residual. That's all. Okay. So this test, as I was saying at the beginning of this video, it moderately rapid, it fast and economical, and the test is used extensively in field soil exploration programs. Okay. This is just for your information. You can read it also if you want. And the test gives good result in soft and medium stiff clay, and gives very excellent, excellent result. Very excellent is too much. Excellent result in determining the property of sensitive clays. Okay. Now, when you are performing the test, there are some sources of errors. There are some sources of error that you should know. Okay. Calibration of the torque. Okay. If your torque is not well calibrated, it may lead to error. The vane, if the vane is damaged, the blade are not good damage. So this also might be a source of error. Okay. And you also need to keep the rotation rate, as it is said in the standard. Okay. The rotation rate is 0.1 degrees per second. So if that is not properly applied, not properly controlled, it may induce some error. Okay. So the thing is, in actual design, actual projects, the undrained shear strength measured from this test, Vane Shear test, are sometimes considered like too high. Okay. Let's consider that this Vane Shear test, this is the estimated undrained shear strength from Vane Shear test. Okay. So they are considered too high. For that reason, it is recommended to correct them using this correction. Okay. Just multiply it by this factor, correction factor. Okay. So the corrected undrained shear strength is equal to this coefficient multiplied by the measured or the calculated from the Vane shear strength, the Vane shear test. Okay. Easy, right? So what is the value of this lambda, this coefficient? I will put back this equation, this formula here. There are several correlations giving this this factor, okay, the most commonly used one is the one from this, okay, and there are a lot of people who did research on how this coefficient affect the comparison, okay. So here is the value of this, the equation for this lambda according to this reference, okay, 1.7, okay, minus 0.54 log unit plasticity index. This is plasticity index, okay. Soil mechanics one, you should know that. I think you know. If you don't know, please check my soil mechanics class and you will see what is the meaning of this one. Another reference is giving us this equation. Depending on the value of the plasticity index and liquid limit of the soil, okay? Plasticity index, liquid limit, these two formula. So I recommend you to use maybe this one, okay? This is the most commonly used formula to correct your undrained shear thing. So this test, this field vane shear strength measured from this test can be also correlated to obtain few soil parameters, especially the soil parameter related to clay. Very important for if you are dealing with clay, okay? So we can obtain, for example, the pre-consolidation pressure and over-consolidation ratio. These two are very important when you are dealing with clay. So this reference, by using 343 data points, they derived the following empirical formula to estimate the consolidation pressure of natural clay, okay? So you already know how to calculate the field and drain shear strength, not corrected one, okay? If you calculate that, multiply it by 7.04, okay? Power, this one, sorry, maybe first power 0.83 and multiplied by 7.04, and then you can obtain your pre-consolidation pressure. Okay, I hope you know what is pre-consolidation pressure. Okay, this is the maximum stress pressure that the soil have experienced in the past. Okay, so if you have, yeah, of course, this is kilonewton per square meter and same unit. Okay, this one, as I said, the field vane shear strength calculated from the top. So the over-consolidation ratio now can also be obtained from this field vane shear strength. Okay, over-consolidation ratio can be obtained using this formula. You have the field and drain shear strength here, and the pre-consolidation pressure, the one we calculated here. That you need this coefficient beta. This beta, yeah, of course, this one is, sorry, this one is effective overburden pressure, not this one. This is sigma prime C. This is sigma prime 0. Sorry, my bad. I didn't see here is O, here is C. It's not same, okay? This is, you can calculate easily this one by, if you know the unit weight of the soil and the depth, you can calculate this one easily, okay? So you have several values of this beta, okay? The beta is the magnitude of beta is obtained by several references. Several references are giving this value of beta. Okay, this one first, using the plasticity index. Another one, this one using water content. Okay, another reference using also plasticity index. So as you can see, plasticity index is a very important parameter you need to estimate soil parameters from the field Vane Shear test. Okay, I think that's all for this video. So thank you very much for your time and see you very soon. Thank you.